Greetings everyone, and thank you for joining this Woodworks webinar on the Life Cycle Tower 1, or LCT-1. This webinar is about an example of a new way of designing and building that was initiated by a builder rather than the architect, the engineer, or the product manufacturer. This building, which we call LCT-1, or the Life Cycle Tower 1, was developed by a large Austrian general contracting firm called Romberg Bau. Their goal was to find a way to build resource and energy efficient buildings based on the life cycle of buildings. So they performed the research and developed a system of design and construction, which I'll describe. To bring the system to market, Romberg Bau established Cree as a company to promote the system. In North America, we are called Cree Buildings, Inc. Cree built LCT-1 as a demonstration project in Austria. That's what I'm going to present to you today. After describing the life cycle tower system and LCT-1, I'll then explain how the system can be adapted in North America to design and build high-performance buildings. But before I start, I'd like to show you a quick time-lapse video of how we erected the building. I feel this video can give a good overview of what I'll be discussing before I break it down into details. You can actually find this video on YouTube or also on our website. So this is a time-lapse video of how LCT-1 was erected. It's an 8-story office building. While the foundation and the central core were being built on-site, the walls and the floor plan panels were produced off-site. Once completed, the prefabricated elements were delivered to site and the building enclosure was assembled. First, the facade elements for each floor were installed. Once all the walls were up, the floor slabs then are placed on top of them, floor by floor. It took 8 days to install 8 floors, and all the work was done by 5 carpenters. The facade elements are delivered as completed wall panels, which include the framing members, insulation, windows, sheathing, vapor barrier. And the floor elements are hybrid slab. These are wood concrete slabs, and they were also prefabricated into one element in the shop. Here's a close-up of one of the floor elements and then the wall elements. Now you're going to see the carpentry shop where the facade elements were produced. They're produced flat on tables. Once the frame is completed, the panels are stood up to install the windows. All the joints are taped airtight to optimize the energy efficiency. The panels are then stored and when ready, loaded onto trucks and delivered to the site. Here are the floor slabs. They're made up of 4 wood beams, 2 at the end and 2 in the middle, with concrete poured around them to create a diaphragm. You can see there's 4 holes in each corner of the slab, and these are needed for the assembly, which I'll describe later. Next, we're going to look at the precast concrete facility where the slabs were produced. The wood beams were ordered from a lumber company who cut everything exactly to precision using CNC machinery. The beams were then delivered to the precast facility where they're laid in metal formwork. The reinforcement is then installed and concrete poured. The next day, the form can be opened up and the next slab produced. All the wood used is engineered lumber. It's all finger jointed and laminated. This wood is stable, it won't shrink and it won't twist, and can be cut precisely. Engineered lumber uses smaller wood sections to create larger elements. This is a method to manage the forest, allowing healthy trees to grow while removing older or damaged trees that no longer absorb and sequester carbon. The system of design and construction allows for lighter buildings using wood as a renewable resource. They're made into panels that can be assembled quickly without disturbing the neighborhood. Each story is assembled watertight and airtight, while emphasizing the beauty and warmth of the wood, which is a natural material. This is much different type of office building than we're used to. For LCT-1, a recycled aluminum rain screen was installed on site. LCT-1 was designed and built to a very stringent energy standard called the Passive House Standard. Using the LCT system, each building has an individual design and can look completely different, but all are resource and energy efficient. So to explain to you all of that, I think the best way to do that is to first introduce myself and introduce to you how I was introduced to this whole system. I'm actually an architect in Berkeley, California. I went to UC Berkeley. I was licensed here. My wife is Austrian, and in the early 90s we decided to move to Austria so that she can be with her family and our daughter can get to know her mother's home. I ended up becoming a developer rather than an architect, and I found this old barn that we turned into 15 condominiums. And this was then my introduction to timber construction and energy efficient design that is kind of very standard, normal in Austria. You can see the building over here on the bottom left. I did the design actually by hand. The carpentry company took my drawings, put them into a computer, and then delivered the parts exactly like they said. All the wood was already pre-cut and pre-drilled, and a lot of the panels were already assembled together. At the time in the 90s, this was a standard called open wall standard, where the wall itself was not insulated, the windows were not in, and it was a low energy standard. And you can see the completed building here on the bottom right-hand corner. We then, with that same company, we kept improving the system, and at some point at the late 90s we began to sell houses to Ireland, and their system had then advanced. The same carpentry company then was making closed wall panels where they already had the walls insulated. They would install the windows and then made the houses in Austria, put them on trucks. We flew the carpenters to Ireland, and then we assembled the houses in Ireland in a week at a time. Then I decided to come back to California and to Berkeley and introduce the things I had learned. And one of the first things I did was I had a house in Berkeley that I didn't sell, and we ended up remodeling that house to the Passive House Standard. That's the same energy standard that LCT-1 is built to, and it's a standard based only on energy consumption, and it's this whole strategy of how to reduce the energy consumption of building. Through this project, I began to work with the Austrian Trade Commission to be able to help Austrian companies to come to the U.S. and promote their energy efficient systems, their products, and their systems of construction. And that's how I began to work with Cree and help them promote the LCT system. So the life cycle tower system is something that was developed by Romberg Bau. Romberg Bau is a large general contracting firm in the west side of Austria. It's a fourth generation company, so they've got a lot of know-how in that company and many people that have a lot of experience with construction. And the current CEO, Hubert Romberg, kind of wanted to do a better job of construction and wanted to make all his buildings much more sustainable. He knew that we were using too many resources out of the earth, and he was looking then at way not to only make buildings more resource efficient, but also how to make them energy efficient. And they looked at the trends of how we are living, how our cities and countries are growing, and there's definitely a trend to move towards urban areas, that we need denser cities, closer to rapid transit systems so people don't have to drive everywhere and we have everything accessible. And so that's one of the ideas, is how can we actually come up with a new system for urban areas, but made more out of wood, a natural resource, a renewable resource, than always relying on concrete and steel only and products coming from fossil fuels. Also, when you look at the infrastructure and the buildings that we have and the performance of the buildings, it's pretty well known now that the building industry is responsible for a lot of the consumption of resource, the emissions, greenhouse gas emissions, the consumption of energy. So in general, the building industry right now is not performing very well, and it's responsible for a lot of our climate issues. And also the process of building is very chaotic. It's still very manual. It hasn't improved. The process of making buildings is nothing like how we make cars or how we make computers. We still go over schedule. We still go it's still expensive. And on top of that, they're not actually, the buildings are not performing very well. So Romberg Bau decided, well, they're going to start a research project and to come up with a solution of how they can resolve a lot of these issues. And this is how the life cycle tower kind of process and concept was invented. So Romberg Bau put a team together to come up with a solution, and part of the members of the team were Arab. It's a worldwide engineering firm, an international firm. They have their main office, one of their offices in Berlin, and they're the specialist in timber. They've worked also with Hermann Kaufmann. He's an architect in the same province of Austria that Romberg Bau comes from, and Mr. Kaufmann is a specialist in timber construction. He also grew up in the Alps. Everybody in his family is involved with timber and wood, so he's got a lot of know-how. And one of the other members of the team is Vihag. Vihag is a lumber manufacturer, and all together they put their heads together and they came up with a system where you can actually go up to 30 stories, up to 100 meters, for a tall high-rise wood building. It's all prefabricated using a modern industrial process, and it can also meet the passive house standard, and if the client wants, it can even be a plus energy building where it actually produces more energy than it needs. To do that, the life cycle tower, basically what was developed was a building system, a system that you can we like to talk about it like my computer. I look at it, it says on it Intel Inside. This is the little chip that operates the computer, and every manufacturer that has a computer just uses a chip and then designs the computer the way they want, different color, different size, different speed, different performance. The idea was, how can we do that with the building, for the building industry with a new wood system? And so the main part of the system for our building is, with tall buildings, you always have in the middle of a building a core. This is a stiffening part of the building. It's like the flag pole versus the flag itself. It's very stiff. It takes all the forces to it. And in that core, you usually have the elevators, the stairs, the shafts, the bathrooms. And then on the exterior of the building, we have glue lamp posts. You can see him here on the outside. They're carrying all the gravity loads, all the load going down to the ground. And then we developed a hybrid slab system that you saw on the video. And this is a slab of wood and concrete. And basically the slab spans from the exterior walls, sitting on two posts, and spans to the center of the building to the core. And this is where all the forces are transferred then to the slab, and from the slab to the core and down to the ground. So that's kind of the Cree inside of our system. Additionally, then we are able to design and add to this the facade, mechanical systems, electrical system, fire sprinklers, alarm system, all the other systems that go into the building. Then our team of technical experts can help then a design team design a building using kind of basically our core and shell. The great thing about this is, when you look at it, the amount of timber necessary to build a 30-story high-rise, the structural lumber for that is about roughly 5,000 cubic meter of lumber. And we found out from the Department of Agriculture what is the annual growth of our forest in the U.S. And if you take all the trees that are growing and see how much wood grows every year, a 30-story high-rise would grow in the U.S. forest in 3.5 minutes. And this is growing from the sun. So, and it's renewable. It keeps, every 3.5 minutes we can have enough wood for another building. So to come up with with this product and why we want to do it, and the kind of the motivation behind it, the idea behind it, is to look at the life cycle of building, the whole cycle from starting with the material selection. Everything starts from the earth, from our natural resources. So we have a choice of, you know, taking things that grow above the ground like trees, or going under the ground and under the ocean to get oil, to get coal, natural gas, burn it all to make big machines, and so on. So we have a choice of what do we want to choose. Then how do we get, then once we get this natural material, how do we manufacture into a building product? What kind of effect in terms of energy, resources, waste does that have to turn our resources into posts and beams and just building products? Then how do we go through the process of assembling all these products and making buildings either, you know, first off-site and then on-site? You know, what kind of impact, environmental impact does that have? Once the building is completed, the next step is people move in during occupancy. How much energy, how efficient is it, how durable is it, how often do you have to pay money to maintain it? So this is the kind of, at the moment, this is the one area of our buildings that actually use the most energy. And then at the end of the life of every building, you know, what you do with it, you just demolish it, you dig a hole in the ground, throw everything into the hole, and then start all over again at point one and start with new materials? Or can you design buildings in a way that at the end of the life of the building you can actually recycle the materials and reuse them? So that was the idea behind everything we were thinking. And some of the things sometimes are not so simple to look at or to understand. One of them that we talk about in Austria is the ecological backpack, is to look at some of the products that we have, and when you see how much they really weigh, like a pair of jeans or a cell phone and so on, but then if you add the weight of all the materials that were needed to actually make that product, it turns out the weight of that product is much more, and it has a much higher economical backpack than we used to. Like a cell phone weighs 0.3 kilograms, but in reality it's 500 kilos that it's carrying. The other thing we always talk about is urban mining. You know, we don't always have to mine the earth. We have already mined it once. A lot of the products that we came out of are already in our buildings, and so why can't we just find a way to reuse a lot of these buildings for other things? And that's basically the beauty of wood, and why wood is such a great product. Because when you look at the carbon, kind of the forestry carbon cycle of wood, it's very sustainable. It's carbon neutral. On one side here you have things that emit carbon into the air, so it's either factories and cars and so on, but also trees. Old trees, once they, you know, when trees are young, they're absorbing carbon, they're giving us oxygen, and they're growing fast, and they're kind of really working for us. But they're also natural like we are. Once they get old, they can't do that anymore as well as they did when they were young, and if we just let them die, all the carbon that they've taken all their life and goes back into either into the air or into the ground. So it makes sense to then cut these trees and in their place plant new trees. And that's one of the laws in Austria. If anybody wants to cut, any forester or farmer wants to cut some of his trees, he has to first get a permit and show that he'll be able to plant 3 trees in its place. And from all these trees, from the 3 trees, and in the next few years, you'll take out the worst ones, the ones that are growing as well or making shades on the other ones. And from all these trees that you take out, you can then make engineered wood product like we showed into the video. And with these wood products, they're different than dimensional lumber in that they're already dried, they won't shrink, they won't twist. And then we can use these modern equipment to be able to, through CAD programs and CNC machinery, digitally feed wood to machine, have it cut exactly to very high tolerances, and then be able to build houses off-site in panels that are very tight. And that's the best way to make energy efficient building, is not have buildings let air escape through them. And then with wood buildings, at the end of their life, you could either reuse the wood for other things, but at the worst case scenario after that, you can break down the wood, stick it in the oven, and that creates energy. Then you can make heat from it, you can heat water, you can make electricity. So this is what makes the wood carbon cycle kind of very effective. And this is an example of embodied energy and what it takes to compare like cement, steel, and wood. And cement weighs about 150 pounds of cubic feet. It takes 142 kilowatt hours per cubic foot to produce cement, and then it lets out over 2,000 pounds of CO2, which is pretty high. When you look at steel, it weighs more, 485 pounds per cubic foot. It needs also more energy, 250 kilowatt hours per cubic foot to produce. It's a little bit better with the CO2 emissions. It's about 1,250 pounds. But if you look at wood, wood is much lighter, 28 pounds per cubic foot. It only needs 5 kilowatt hours per cubic foot to produce. But then at the end of the life, you can then heat with it and create energy, which makes then carbon pretty much, wood pretty much carbon neutral. And it's all from the solar energy from the sun. So here is just some examples then of some of these modern wood products that are coming on the market. Some you're already familiar with, blue laminated timber. It's all made out of smaller pieces of wood to create larger pieces. Finger jointing of wood members to make them longer. This is a new product coming on the market called cross-laminated timber. This is large slabs of wood that come in 3, 5, 7, 9 layers, and they can come up to, this is solid mass timber, come in panels of about 30, 40 foot long, 8 to 10 foot high, and anywhere from 4 to 11, 12 inches thick. Different manufacturers have different system of making them, and this is a material that can also is becoming popular because a lot of our forests here, and especially on the west side of the U.S., have this mountain beetle infestation, and there's been research done that this is a good solution to actually take this wood out of the forest before it all burns and turn it into a building product. With all these unstable wood materials, then we have a modern way of working with it, starting with a CAD program that the architect draws or the engineer. That wood then can be sent to a machine. It's cut exactly to very high precision, exactly like the drawing shows. And then this process of industrial manufacturing that we're already using to make cars, to make computers, to make furniture, make refrigerators, we can use the same type of system, making panels together on tables. There's even some of the bigger companies have ways to also flip the walls over so you can work on the back side of it, and then you stand them up and then add the windows, the siding, and so on. Different companies have different ways of doing it in Central Europe, but it's a lot of it is, they use much more prefabrication than we do here in North America, and they also are able to make closed finished components. This is then an example of how you can bring an entire wall and place it in this place, including insulation, windows, and so on, floor elements, roof elements, and even it's easier to then to make mechanical system, have them prefabricated off-site and brought on-site. So after Cree, this was a motivation and the idea and basically what was going on in their country in terms of the wood industry and carpentry, advanced carpentry products and systems of work. They decided they wanted to come up with a product that they can put on the market. And when you analyze how we build buildings and how we deliver buildings, we have the original system. The traditional system is what they call design, bid, build. You have an owner, then you have an architect, and then you have the builders and the estimators. And it's like up and down the chain. And that system, has proven it doesn't really work. As I said at the beginning, the buildings are not performing. They're using a lot of energy, a lot of resources. They have a lot of defects. The price overruns, scheduling overruns. So we're trying to look for a better system. This better system now is called the integrated design process, where if a client is informed and wants a better building, he puts the whole design team together at the beginning. He understands he has to pay a little more money up front, but at the end he's going to save a lot of money, and that whole design team kind of works together to design the building. But when we looked at that building is also a prototype. All of our buildings are one of a kind. And so Cree wanted to come up with a system where we can integrate a lot of this design process in-house and come up with something where, maybe people see in a building or don't see, but we don't have to create it every single time, that we have a system that can be used. but then make every building different, different heights, different lengths, different appearances, but they know that they will perform because the backbone of the system is already proven. And so in our case, then for these tall wood buildings like the life cycle tower, we have a core. Then again, this is the stiffening part of the building. That core, from the research that we've done, we feel confident from an engineering and seismic and fire point of view that it can be made out of wood. It might be a little bit too early to have building departments accept that. So it could also be made out of concrete or steel. And on the outside of the building, then we have the glue lamp posts. These are the bearing posts. They're bearing all the loads up and down. And then attached to that are our slab system, our hybrid slab system. This is where we've spent most of our time and money to research and come up with a solution for these slabs. And then additionally, what we can add to the building is then our facades. The facade in our life cycle tower office building is what we call a curtain wall. It's not load bearing, it's not carrying any of the loads, it's just attached to the post, so it's just hanging on the outside, kind of a jacket on the whole building. And on that facade, then you can add different elements, from solar elements, shading elements, the windows, the insulation, green walls, anything that the client and his design team would like to have. And for the interior of the building, also with our technical team, we can help with the design team and optimize all the systems so that they all work together, from the facade itself to the heating and cooling and ventilation and lighting and so on. So to start, and actually the product, we built a small little building as a prototype to see what it was like, and we assembled it and also disassembled it to see how it could work. While at the same time, we ran a series of fire tests, because that's one of the most important things. When you use wood, there's still some fear that wood burns. But what we found is wood does burn, but it burns very predictably. We already know it's actually in the codes, and it basically says in the codes, for every 1 hour fire protection you need on a piece of wood, you need to add 1.5 inches of wood, because that's how long it takes for 1 hour of wood to burn when you have heavy timber, big pieces of wood. And we found that when we did run the fire test, well, we were having more problem with the steel and the concrete. You could see here inside the fire chamber, the steel from the heat would expand and it would crack the concrete, and it would actually create cracks through the slabs themselves. But the wood itself stayed whole, and basically all the wood that we use is designed large. I mean, we know what the structural size needs to be. The wood bigger by adding 1.5 inches of wood on every surface that would be exposed to the fire. And you can see after a series of tests to optimize the system and have the wood and the concrete work together, we were able to get to pass a 2-hour fire test. And the idea of a hybrid system of wood and concrete is that every material has actually its own properties. They don't all perform the same. They're good at some things and bad at others. And so to be able to make these slabs as light as possible, use the least amount of material possible, it was best to then combine the best properties of both the concrete and the wood to be able to make these floor systems that can span 30 feet and carry all the loads that need to carry, and at the same time be able to withstand the fire requirements that are required. And so that's why we came up with a hybrid system. After all of that, we decided that we needed to put up a building to be able to show what we've done, and this is then the story of LCT-1, this office building that we put up in Austria. It was a project developed by Romberg Bau itself on one of their properties. The architect on this project was Hermann Kaufmann, who helped us originally with the research of the project. These are just some images of the interior, the entry. And you can see the building has then a core. This is the stiffening core where you have the elevator, the stairs, the shafts for all the pipes and so on, and the wet rooms, the bathrooms, and so all together in the stiffening part. And then we added the offices around it, only on one quadrant, one to just save some money, but a developer would have actually been able to go 4 times around that around this core. That's how stiff it is. And but this, we just wanted to show what we can do. So we have the offices here attached to the core, and here is an example of where, in terms of design, we can extend away from the core and still be able to add to the building and not always have to support things only on the core. So those are part of the design of the system. You can see one area of the entry is 2 stories, just the entrance, but altogether it's 8 stories. And so this is just a kind of little more detail on how we actually build the building together. So here is the central core of the building. The building department required us to build that out of concrete, so we did. So the foundation and concrete were built on site, and off site then we're actually making the wall facade elements and the floor elements. And this building was built in Austria according to the Austrian seismic and requirements. And so we've actually adapted this to the US, which I will show you closer to the end of the presentation. So here's just showing the slabs being made off-site. So we bring the wood to this precast concrete company. We have the metal formwork that opens and closes. We put the wood in, we put the rebar, we pour the concrete, and then the next day we can open the slabs and store them. At the same time, we were making then the carpentry, the wall systems were being made in a carpentry shop. And here you can see they're all heavy-duty glue lamp posts. And the way the system works, at the top of every post there's a metal tube, and at the bottom of every post there's a plate. The ground floor posts have just a flat plate with holes that you can just bolt it onto the foundation. But once you get up higher, these plates have pins in them. And basically these tubes on the top here have a little hole in them, and at the end this pin goes into the hole. That's how we're able to assemble things really fast. So here's the carpentry company that's making them. So you can see there's the double posts here, the load-bearing elements, and here's the wall that's not load-bearing. You can see the lines here, it's made from engineered lumber. Even all the studs themselves are made from engineered lumber. This is a thicker wall, thicker than we would build in California, but in Austria it's a cold climate, so to meet the high energy demands or to reduce the consumption, you need more insulation. You can see the carpenter is actually putting this together on a table, and here is one of the panels that stood up. You can see the posts, the load-bearing posts with the tube on top, and everything with these yellow lines is a special tape to be able to get all the joints airtight, so there's no energy escapes out of this building. And then the facade elements are stored, and when we're ready, they're put on trucks and delivered to the site. So once we start on the site, all the slabs are there, the core is ready, there's an angles kind of poured into the concrete, metal angles with pins in them to take the slabs, and then we start construction. The first step is to bolt all the ground floor posts into the concrete at the foundation, and then we start bringing the walls. So this is floor number 1. You can see the wall elements come, windows are on, everything is on. Here are the posts with the tubes on top of them. After all the walls for floor 1 are put in, then we start bringing in the slabs for the floor. And you can see the slabs, each slab has a hole in the corner. These holes were already taken care of when we made the slabs in the formwork, and then we can just drop a slab into place, and basically what happens at the wall, we have the angles there with the pins. It sits right through the hole, and this doesn't need to go floor to floor, it's just attached to the wall. But on the exterior, they need to be connected together, and so that's why we have a much longer tube at the exterior wall, and the slab just slides into it and finds its place really quickly. Then once all the floors are put together on one level, if you go up on top of that level, you'll see these tubes are sticking up above the slab, and you can see they're sticking up about ½ an inch or so above the slab. Then we start bringing in the walls of the next floor, and the walls have the pins at the bottom, and basically that pin goes into that hole there. And that's why everything kind of fits together really well. And in terms of connection, we have a metal plate sitting on a metal tube. That's where everything is bearing metal to metal. But we have wood from floor to floor, kind of separated also for fire reason, but by concrete in the middle, but everything is actually bearing on metal. This is just you can see the floor below, the different slabs. The next floor is going up. Everything as it goes up has to be, very plumb, very level, so that everything fits. And here is an example then of where we were able to extend the grid. This is the corner of the core here, and then we have these concrete beams also sitting on wood posts, still the same system with the tubes that it slides into, and then we can bring in the rest of the slabs. So as soon as we put up a floor, the building is watertight, airtight. There's a lot of exposed timber in it. It smells really nice. It feels very comfortable. It's warm. And this is then an example of the office building now, how then we finish the ceilings and the floors. This is actually one of the top floor of this building is now the Cree office. So here's just kind of a quick way, day by day, how every day, a floor went up. Even the carpentry company had on the 5th day, where on Friday before the weekend, there was a chance of rain. They had a temporary roof that they put up in 15 minutes just to cover the building, and then took it off Monday morning and continued going up. This is then for this building, the building department didn't allow us to use a wood facade, so we ended up using a recycled aluminum facade that we actually installed on site. We could have put it on in the factory, but the aluminum was very thin and it would have been damaged, so we ended up deciding to make that on site. So in terms of design and what I was saying earlier, our system, the Cree inside, is made out of a post and beam system and kind of a core and slabs. And so in terms of design, there's several ways of building a building like this, and this is up to the design team and the owner to come up with their own design of how they could do it, but the parts of the building are always the same. So there's one core with 2 cores, it doesn't really matter what it is. It's just up to, there's flexibility in terms of the design. Even though it's a system, it doesn't mean that all the buildings look the same. Actually, all the buildings built to the system up till now all look completely different. You can also have interior light wells in the middle of the building. It's really all up to the design team to use the elements that we came up with and design the building. Another advantage is when you look at the life cycle of building, because we have a 30-foot span from the core to the outside walls, all these kind of interior non-bearing partitions can be added and removed easily. So the core is still the same, but this time we can change the building from a hotel to an office. The building begins with one use in mind. 10, 15 years down the road, it could be that that neighborhood changes and that use is not really the best for this building. So you can easily have access to all the systems of the building. You can take them out and replace them and change the use of the building easily without having to tear it down. It's not working. So while we were building LCT-1, Herman Kaufman, the architect who designed the building for us, he has his own architecture firm, and he has other projects and takes part in the design competitions. And this is one project where it was an international design competition for an office building that he designed, and he won. And only after he won the competition did he tell the client that, well, the building was designed using Cree's life cycle tower system. So this was the second project that we built. This one is only 5 stories, but it's a very long building. Now altogether in square feet, it's one of the tallest, largest buildings and wood buildings in Europe in terms of square feet. Its design is a little bit different now. It has 2 cores instead of 1, and then you have these 2 ends of the building that are away from the core, like cantilevered away from the core. So these parts of the buildings then needed to be tied together and to bring the forces back to the core. And this is when we began to come up with other solutions that are similar to kind of the seismic solutions that we need here in California and on the West Coast. But you can see the building in the middle here, then the design is with steel posts and beams, and then the slabs are supported, and there's 2 different size slabs. This is a little bit off center, so we have the walls on the outside, exactly the same idea. The posts and then the wood concrete slabs are then bare in the middle and on the outside walls. And then the MEP system, the mechanical and everything, comes from the basement up into the core and then through these drop ceilings to all the rooms. And here's an example of the carpentry. The same carpentry company built all the facade elements for here. And in this case, though, they decided not to put the windows into the walls because the windows were much larger for this project. So they built the walls in two sections. Here's the load-bearing part with the insulation and the posts, which are the ones that you can see here on the left. Then they brought in the slabs, bearing on the steel in the middle. And then here you can see then what it looks like, similar to LCT-1. And then they brought in the second part of the wall where the windows are in a frame, and then those were dropped in place as soon as they were finished with the floor. So you can see it's kind of the same system, but a completely different looking building. And this building is over 120,000 square feet of office space, and the building enclosure, after they finished the core and the foundation, we put that up in 6 weeks. Here's some images. Now, pretty soon we're going to have finished images. So now that we're here in North America and with an office in San Francisco in the Bay Area, we decided to adapt the system to our standards here, and we've been working with Arab, the same international engineering firm that helped us originally with the research. In terms of fire, we're defining this building as heavy timber. And this is where it falls into the codes, under that section of the code, and where then the structural members are oversized so that for fire protection that they have this additional wood to protect the structural parts. And in terms of seismic, we're kind of trying to make it fit in a system that's standard, that we don't need special permissions to actually have it work and have it accepted. So we just want something that's innovative but fits within the code so that we can build here. And you can see the difference that the heavy timber versus light framing. The heavy timber is much bigger pieces of wood. One of these pieces of wood burns, it chars basically, and so the structural member stays inside and it still can carry the loads of the building. But the traditional way that we build in wood is with the stick framing, and then this is almost like adding fuel to the fire because they're smaller pieces of wood and they will actually burn really fast. So we came up with a generic solution for a building here under our seismic area, and when we took all the code considerations, we ended up having a building with 2 cores, and just for also the exiting requirements and the fire requirements of a building. And but additionally, the 2 cores lower a little bit the forces that have to come to each core. And basically, in the middle, we have a section that will be like a corridor that's also sitting on wood posts in the middle, but this section is only concrete where we can run all the mechanical electrical systems. And then from the inside to the outside, it's then again the same slab system that we've used in Austria with the wood concrete hybrid slabs. Then Eric ran some modeling, some simulation of the forces that will be on the building, and basically they saw how the building can actually move as much as needs to be during an earthquake, but still not come apart and come back in its own shape. So what we had to do is find ways to connect things together differently than we did in Austria. This is one idea, was how to have the slabs get bolted together so that they can stick together more, and then at the end we just fill this little hole with some non-shrink grout. And then we came up with a system that where again the posts and beams and the tubes kind of fit together. It's allowed to move and to transfer forces from the post to the slab, the diaphragm of the slab, to the core, where then, but without things coming apart. They could move, and that's kind of the advantage of wood. It's a little bit flexible, and so it won't break and can transfer the forces. This is another example with another architect we work with for a project in Oakland. They're trying to rehabilitate a whole neighborhood, and we suggested, well, maybe we should start with something with wood and show new technology and new kind of sustainable ways of building. So without taking too much time, the architect was able to take one of the buildings on the drawings and quickly change it to fit the life cycle tower system, again with the cores and the slab system and the posts. And then we came up with then the solution of how to tie these slabs together all across and how to put some reinforcement around and create kind of like a belt around the building to keep everything together for our seismic area. Then, because we are general contractor and basically we are the ones that will build the parts of our system, we also have one person on our team who is a supply chain manager. He comes out of the auto industry. He knows how the auto industry makes things, and we're trying to then use the same kind of technology to make our building. So here's then the example of how we make the slabs. We order the wood here from the lumber manufacturer. Everything is cut exactly as the drawing says because they have CNC machinery. The wood company itself attaches and whatever metal fasteners go into the wood, like whether it's screws or anchor bolts and so on. These get dropped into the metal frame, like you see here, and then we order then the reinforcement. The reinforcement gets placed into this inside the formwork, and then the concrete is poured. And the advantage of that is we could start earlier and then store the concrete slabs and let the concrete cure, and that we don't have to wait for that on site, and we don't introduce so much moisture into the building, which is also not a very good strategy. Then here, as you can see, the carpentry company is making the walls, which I showed a little bit of that earlier. Here are some of the walls. I make them on tables. I stand them up and load them. And then here's some of the work that we've done for the mechanical, electrical, and plumbing. This is eventually these buildings will be like plug-and-play buildings that all the systems that go together can be manufactured and brought into the building and placed in place, but where they can all be accessible the way we have it designed. You can drop down, you can fill the space between the beams with all these different systems, but also the doors are hinged where you can actually get right up into it, and 15, 20, 30 years down the road, if there's newer system, better systems, and it's easy to replace them without having to tear the whole building down. In terms of performance, when we compared a wood building like this with a reinforced concrete building, this is some of the work that we did during the research phases. We found in terms of cost, there really was hardly any difference in cost, especially now that this is very early in development stages, so not very many people know how to really build like this. But when you actually compare the CO2 emission of a concrete building versus a wood building, the wood building is over 90% better because this is a renewable resource. It doesn't take much energy to make. There's trends in the wood industry, and Woodworks has been one of our companies are trying to promote wood system and promote us, but there's things going on all over the country. In British Columbia, they've already increased the height of wood buildings to 6-story. This is for wood frame residential buildings, so that's already in the codes that you can go up to 6 stories. This is just a press release from the U.S. Department of Agriculture, and they talk about trying to build, the U.S. Forest Service, that they want to use innovative wood systems and materials for all new structures over 10,000 square feet, that they want to reintroduce wood products into all aspects of the next generation of buildings. So if you want, you can have access to the presentation and read a lot of this information. This is also in Oregon. They were trying to pass a bill to use wood first, and in the act itself, they listed all the advantages of using wood and why it makes sense for us as a country to introduce more wood into our building industry. This is just some examples of these new cross-laminated timber that I mentioned before. The tallest building to date, or up to like a year ago, was a 9-story wood wood residential building in London, made out of cross-laminated timber. And there's now, just recently this year, a 10-story building was built in Melbourne, Australia. So new wood products and new wood systems are being introduced across the world. Basically, there's a race to go as high as possible. Cree took part in a competition in British Columbia. We ended up actually placing second. Michael Green won this competition with also his innovative wood system, and basically it was a project to introduce new ways and new designs and technologies of working with wood. And within a few months, we worked with a Canadian team from architects, developer, general contractor, code consultants, fire consultants. All together, we came up with using a Cree system and designed the building. Again, looks completely different than any of the other buildings, but when you start looking into the inside of the building, you can see, and here's an example, it's the same idea. It's a glue lamp post and slab systems. And so we do have a system that is flexible in terms of design. You can build any building with it, but one thing you can make sure of is you'll get a building that is resource efficient, energy efficient, and will perform as promised, because we have a system approach that we can keep repeating and repeating and improving on. And our goal is to make buildings perform better. Thank you very much for your time, and now I'm going to end this presentation. And if you would like to send me any questions, please feel free. Here's my email address and our website.